All right, welcome. Today, we're diving into what is basically a mathematical detective story. Our mission? To crack a secret code that's hidden deep inside one of the most beautiful and complex things in all of math, a fractal.
And this is our subject, this absolutely stunning, enigmatic structure known as the Aether fractal family. Now, you know how fractals work, right? It's a world of infinite complexity, patterns that repeat forever. But this one is holding a very specific secret, a precise mathematical rule that's had researchers stumped. And today, we're going to uncover it.
So here's our game plan. We'll start with the enigma itself. Then, we'll look at a formula that gets so close to the answer, but has some flaws. After that, we'll open up a special toolkit to analyze those flaws, use it to crack the code, and then we'll zoom out and see why this is a much bigger deal than just this one fractal.
Okay, let's kick off our investigation. What exactly is the mystery that we're trying to solve here? Well, it all comes down to something called the area law. Just think of K as a dial that you can turn to change the fractal's shape. As you turn it, the total area of the fractal changes, and it follows a specific rule. Now, the formula we have is a fantastic approximation, but in mathematics, approximately just doesn't cut it. The real prize is perfection. And that is the heart of the problem. Hidden somewhere in all that beautiful chaos is a perfect, precise relationship. Our approximation misses these tiny, super subtle corrections that would make the formula totally exact. Our mission is to find them.
Every good mystery has a clue that seems right on the money at first, but is actually hiding something. In our story, that misleading clue is the first attempt at a perfect formula.
This was the best guess mathematicians had for a long time. It's a really powerful tool called a Poincare asymptotic series. What it does, essentially, is it tries to reach perfection by adding an infinite number of those tiny corrections we're looking for. And for a while, it works brilliantly. But it has a fatal flaw.
The way it fails is actually fascinating. See, this kind of series is like a sprinter who's running incredibly fast towards the finish line, but then just veers off right before crossing it. It gets closer and closer and closer to the real answer, but because it ultimately diverges, it never actually lands right on it. So yeah, an incredibly powerful tool, but an imperfect one.
So here's the crucial point. The problem isn't that the formula is wrong, it's that it's incomplete. And its very imperfection, the way it fails to be exact, well, that's not a bug, it's a feature. It's a clue. The series is actually hiding information, pointing towards a deeper truth that we just can't see yet.
Now, to find that hidden information, we can't use our usual methods. We need to break out a specialized set of tools, almost like a mathematical forensics kit that's designed for exactly this kind of problem.
And that toolkit is called Resurgence theory. It's this whole philosophy built around the idea that when these powerful but flawed series break down, they don't just fail randomly. They fail in a very specific way that actually reveals the exact information they were missing. It's almost like listening to the echoes of a formula's failure. The main tool we're going to pull from our kit is the Borel transform. If our original series is like a blurry, out-of-focus picture of the truth, then the Borel transform is the special lens we can put on it. It transforms that series into a totally new mathematical object, and in this new form, the hidden information just suddenly snaps into focus.
All right, this is the moment. We've got our flawed clue, and we've got our special lens. So what happens when we finally put them together?
And wow, this just brilliantly shows the power of our new tool. We take that complicated, infinite, diverging series, we apply the Borel transform, and it simplifies all the way down to this, an elegant, clean, and beautifully simple function. All of that chaos has just been distilled into this one expression, and the secret we're looking for is now sitting right in front of us. So, where's the secret? Just look at the formula. If you try to plug in the number 1 for s, the bottom part becomes 0, and the whole function just breaks. This breaking point, this singularity, it's not a mistake. It's exactly where the math has encoded all of the hidden information.
This right here, this is our aha moment. The location of that breakdown is the treasure map. Everything our first flawed formula couldn't tell us is packed right into that one point. We just had to know how to look for it.
And when we analyze that singularity, this is what falls out. A number called the Stokes constant. This single, precise value, 2 times the square root of pi. This is the key. It's the missing piece of the puzzle that lets us correct the original flawed series and build a truly exact formula. The code is cracked. So, we solved the mystery for the Aether fractal. But the story really doesn't end here. As amazing as all this is, the real power of this technique is that it doesn't just work on this one problem.
I mean, this represents a huge leap in how we think about these things. We've gone from a method that gives a pretty good approximation but hides information to a totally new kind of analysis that captures the exact data. It doesn't just get close, it reveals the hidden mathematical structure and lets us find the fundamental why behind the formula.
And this is why this all matters so much. So many of the most complex systems in the universe, we're talking about everything from the behavior of water and fluid dynamics to the fundamental nature of reality and quantum mechanics and string theory, they're all described by these same kinds of powerful but imperfect series. This toolkit, we can use it on all of them.
The big takeaway here is this. We now have a method for finding perfect, pristine, mathematical order hidden deep inside systems that appear messy, chaotic, and just impossibly complex. It's like a whole new way of seeing the universe.
And that leaves us with a final, pretty tantalizing thought. From the turbulence of the oceans to the frontiers of theoretical physics, there are countless systems that have been described by formulas we knew were close, but not quite perfect. So you have to wonder, what other hidden structures and secret codes are out there just waiting for us to apply the right lens? Makes you think. Thanks for tuning in.